Hi, this is Ben Lavasani from National Instruments Applications Engineering, and I'm going to give you a brief overview of a project I've been working on along with my colleagues. We built an interactive showcase of NI products in hope to exhibit the wide range of NI products and technologies in the demonstration of an automated and interactive industrial building. This is a small model of an industrial plant where we put technologies inside and made it interactive so you can explore some of our products. I'm just going to give you a system overview now. So we had various rooms inside the plant. We start off with the power generation and monitoring, where we use the cRIO and the FPGA to control a DC motor. Then we use the LabVIEW real-time and the scan engine to do some PID control of a furnace to keep the furnace at a set point. To control the motion of the lift, we use the FPGA to send signals to the stepper motor driver. Finally, we did some load cell monitoring using the DAQmx driver along with a USB data acquisition device. We use the scan mode with a digital I/O module to send PWM signals to our temperature controlled furnace. A light bulb would increase the temperature of the furnace and a fan was used to decrease the temperature. Closing the loop on this control was a thermocouple input. The outputs were all set using a tuned PID algorithm. In the power generation and monitoring section of the plant, we generate power and distribute it towards lighting the building. This was done by coupling together two DC motors, one powering and one generating. The generating DC motor was used to light the white LEDs in the plant. If the generation falls under 35%, then the red LEDs were designed to flash to alarm that this event had happened. The scales were monitored from the host machine running Windows. We used a DAQmx driver and a USB data acquisition device, which included a C-series module. This C-series module was designed for load cell measurements. This measurement could have also been added to the cRIO, however this shows the tight integration between the different platforms. In the lift section of the plant we utilized the FPGA with a single C-series digital module. This digital module was used to send commands to the stepper motor drive, telling the stepper motor drive which direction and which speed to travel in. We also closed the loop using limit switches, so we knew which position the lift was in. The user interface is made up of the following components. We have the security tab where we can override a key lock with a password and also allow us to emergency stop the plant. We have the plant status where we can monitor what's going on in each individual room of the plant. We have the generator where we can adjust the power that's being generated and also do some monitoring on the power. The furnace allows us to control the temperature of the furnace by setting set points. Also we can adjust and tweak the PID on the fly from here. The lift room allows us to cool the lift and monitor where it is in its position. And then finally the scales allows us to observe what mass is loaded onto the scales. The key lock, when turned on, will trigger the software to lock all tabs and immediately switch to the security tab. This is where the operator can either unlock the key lock or insert a password to override the front panel. An additional feature we implemented in the plant was the emergency stop button. This was used to seize the operation of the whole plant and exit all programs when pressed. We predominantly based our project on our embedded cRIO platform. For a motion demonstration we use a C-series module for cRIO with a DC motor for the power generation and also a separate drive and stepper motor for the lift. Some basic electronics and mechanics had to be produced as well in order to implement our temperature control and integrate our motors with our moving parts. Finally, the integration between our user interface on the laptop and the plant itself also involved USB-DAQ. This measurement was implemented using a single sleeve carrier chassis for C-series modules. However, this could easily be implemented to take wireless measurements using a Wi-Fi DAQ. The tool that brings all of these together, of course, is a graphical system design environment that is LabVIEW. To use LabVIEW and control the cRIO system, we use LabVIEW real-time and FPGA modules. We decided on the cRIO for its real-time processor, reconfigurable FPGA, and C-series I/O modules. Thank you for watching our video on the measurement plant. Hopefully you can see some of the benefits of using National Instruments hardware along with LabVIEW graphical programming for your future projects.